Signals and messages from space aren't anything unusual to us. This time, the structure detected in outer space is massive and impactful. One of astronomy's greatest mysteries is being furthered by bright, brief radio bursts emitting from the neighborhood of a nearby galaxy. One of the last places astronomers anticipated finding the frequent energy bursts was an old collection of stars known as the globular cluster. Fast radio bursts, or FRBs, are extraordinarily brilliant, extremely brief radio wave bursts that frequently originate billions of light years away and have eluded explanation since they were first discovered in 2007. Scientists assume that the bursts are caused by youthful, transient cosmic objects known as magnetars based on their current observations. But a study describing the discovery published on an academic preprint service, RxIV, claims that a fast radio burst observed last year has now been linked to a globular cluster that is 11.7 million light-years away and close to the nearby spiral galaxy M81. This burst was discovered among an elderly star cluster, similar to a smartphone inside Stonehenge, in that the observation makes no sense. This is not a place fast radio bursts are expected to live. Brian Gainsler, an astronomer at the University of Toronto and a co-author of the new paper, posted on Twitter, "Just what is going on?" Cosmic anachronism is challenging to explain, according to scientists. They're also coming to the idea that there might be other ways to create a quick radio burst, just like many other celestial phenomena. According to Cornell University astronomer Shami Chatterjee, who studies the bursts but is not a member of the finding team, FRBs might be just this general event linked with a huge spectrum of probable sources. Using the Canada Hydrogen Intensity Mapping Experiment (CHIME) telescope, which has proven to be a relentless FRB finding machine, researchers first discovered the burst, designated FRB 202000120E, in January 2020. Less than 30 rapid radio bursts existed when CHIME went online in 2017, but the telescope has since increased that number to over 1,000. FRB 202000120E is a repeater, a space engine that emits repeated audio-radio blasts rather than exploding once and disappearing, like at least a dozen other known bursts. Although its bursts are not intense as those coming from beyond the cosmos, where they originate from billions of light-years away, they have helped scientists locate the FRB over the past year. The team could then try to locate a source from there. Astronomers knew they were looking for something close by, possibly even inside the Milky Way's gaseous, sparsely inhabited halo, because measurements of the burst indicated that FRB 202000120E was relatively nearby. Scientists later determined the specific location of the bursts by using a network of radio telescopes called the European Very Long Baseline Interferometry Network. The authors conclusively proved that FRB 202000120E is associated with a globular cluster in the M81 galactic system, thereby confirming that it is 40 times closer than any other known extragalactic FRB, right in the new paper. The interpretation of that is where things get very, very interesting, Chatterjee says. It is very hard to fit into existing models. Some of the oldest things in the observable universe are globular clusters. They are billions of years old, possibly even considerably older than the galaxies they orbit. Until now, scientists strongly suspected that some of the youngest compact objects ever seen, magnetars, or extraordinarily magnetic, flaring stellar corpses generated when young, massive stars explode and die, were responsible for quick radio bursts. When the ultramagnetic stellar corpse is created, it persists for tens of thousands of years before its magnetic field degrades and a regular neutron star is left behind. However, as far as astronomers know, magnetar-producing stars are not present in these brilliant, closely packed globular clusters. This star formation is happening all around the universe, even in our galaxy in many places, but not in globular clusters, says Northwestern University Claire Yee, who studies globular clusters. It's like, wow, what is happening here? Fast radio bursts have been a riddle to solve for about 15 years. Initial theories include alien technology, spoiler, evaporating black holes, flaring dead stars, colliding dense objects, and yes, even exploding dead stars. The radio burst's nanoscale architecture, millisecond duration, and strength hinted that incredibly dense, compact objects must generate them. As a result, scientists started looking at phenomena like black holes and neutron stars, which are left over after massive stars explode in supernova. Later discoveries provide further evidence that some bursts are born in places with extremely high magnetic fields, raising the possibility that magnetars are the source of these puzzling signals. The paradigm that FRBs come from magnetars has taken on quite a life since we saw the FRB-like burst from the galactic magnestar, says Brian Metzger of Columbia University and the Flatiron Institute. You had a situation where the theorists and the observers were pretty happy with magnetars. But that didn't last long. With the discovery of FRB 202000120e, astronomers now need to figure out how magnetars might arise and survive in globular clusters, or they need to figure out how a population of extremely old, quiet stars can generate such powerful blasts. Neither is an easy problem to solve. While magnetars are not considered to be present in globular clusters, other types of stellar remnants ought to be common. Early in the lives of these old clusters, white dwarfs formed when sun-like stars ballooned into red giants and die, and neutron stars, formed by greater supernova, can be produced. It is possible that magnetars can form when two neutron stars crash and merge, when two white dwarfs collide and merge, or when an orbiting companion star of a white dwarf steals enough material from it to collapse into a newborn neutron star. However, nobody has yet observed a magnetar forming in this manner. Yi of Northwestern University believes that additional research is necessary to determine how magnetars can emerge in these clusters and how other stars might be able to generate fast radio bursts. She added that it's also critical to learn more about this specific cluster to determine what else might be causing the enormous blasts. She asserts that globular clusters are distinct, some are denser and some are less dense, and you will observe various outcomes in different clusters. Metzger adds that even in the absence of magnetars, it should be able to produce an event that resembles a fast radio burst. Fast radio burst-like outbursts could be made by two neutron stars twirling around one another, and by turbulent disks of matter whirling around black holes that occasionally produce jets and flares. I'm a little more inclined to believe that he admits something is going on here besides magnetars. Perhaps, like gamma-ray bursts, which puzzled astronomers for decades after being first identified by a military satellite in the 1960s, rapid radio bursts are created by various pathways. Now we know that strong supernova and colliding neutron stars can produce these extremely energetic flashes of gamma rays.